Okay, so for this class, we're going to continue on with our discussion and investigation into our polynomials side of things. Hey Sam, how's it going? Just a quick introduction to how this all works. Got a few cameras set up, one for my face, one for any handwritten notes that we do. You're probably going to want to pin that one. It's just the camera that's focused directly on my notebook. Just right click it and click pin to make sure it's easily accessible there. And the other thing would be the screen share. If you look at the top of your Zoom window, you'll notice the option to toggle between the screens. We'll mainly be talking between either the screen share or the handwritten notes bit. If there's any questions about that, let me know. Otherwise, polynomials. Let's crack on. So this will be in the screen share. So, sketching cubics. So the first kind of cubic that we're going to look at sketching is the cubic that is in the so-called inflection point form. So kind of like how quadratics have a turning point form, cubics have an inflection point form. Namely, it will show you where the inflection point of the cubic is. The inflection point being this bit here, the part where it goes from being concave down to going concave up, or vice versa. It inflects, it kind of wobbles at that spot. So your h and k terms, depending on what those are, will tell you the location of that inflection point. Very similar to finding the turning point for a quadratic. What you're looking at right now is the cubic. So it starts from the bottom left, goes concave down, and then inflects in the middle, before then rising to the top right, where it is now considered concave up. It just kind of wobbles its way from bottom left to top right. Dilation factors work the same way as they always have. So multiplications at the front will always stretch it along the y-axis, or you could be considered, or that could be considered from the x-axis. As the number gets bigger, it'll go further along the y. If the number gets closer to 0, it'll get actually further away from the y instead. You typically don't get dilation factors that are specifically dedicated for the x variable. Those will be located in the b spot on the screen share. The reason why you typically don't see that is because if there is one there, it can always be factorized out. Right, like you can take this b and the cube out of that bracket, and that's just going to condense down into some number. Like if a was 1 and b was 2, that's just going to be 1 over 8. It's just going to condense down into a number, so we typically only ever see this leading term rather than any b dilation factors in there. Reflections, very similar idea. So any negative signs in the function will cause it to reflect, depending on where it's located. With the cubic specifically, the fun thing about this is whether you're reflecting about the y or about the x-axis, both cases are actually identical. And the reason why is based on how the cube applies to negatives. We know squaring a negative number will turn it back to being positive. However, cubing a negative number, negative x cubed, that negative can be factored out, or in other words, just sort of basically nothing actually happens to it because you're having 3 back-to-back multiplications as opposed to an even number of multiplications. Mathematically, we can see that whether we put the negative on the outside or directly on the x, both simplify into the same exact equation. And so what we find is that it doesn't matter where the negative is, the graph is reflected. Jeez, I can't talk today. The graph is reflected in the exact same way. So instead of having the original green graph, we're now flipping in either the horizontal or the vertical axis, depending on how you want to perceive it. Like for instance, you can imagine that looking horizontally, everything is flipped, or you could look vertically and you'll notice that everything is flipped as well. That's referred to as an odd function. All functions that are considered odd functions have this exact property, where you can reflect them in either direction and get the exact same outcome for it. Horizontal translations. This is going back to what I was talking about earlier with the inflection point form stuff. The h term in quadratics would always tell you the horizontal location of the turning point. The exact same is true for the inflection point here. Plus is always left, minus is always right for the x specifically. So your x minus 1, now you're going to have it at x equals 1. X plus 2, you're now going to have the inflection point at x equals negative 2. Vertical translation, that's just the plus at the very end of the equation. Again, that works the same as quadratics. This would be a vertical shift up by 1, and sure enough, the inflection point will follow. Same thing with the -2. Those are all the basic transformations that are applied to cubics. They're very similar to quadratics, except the shape is a little bit different. There's nothing crazy like asymptotes, or if you were here for the exponential stuff, there's no that's also an asymptote, actually. There's no other strange key features to watch out for. It's very much the same as all the other stuff you'd be used to by now. Any questions on how any of those key features work? Cool. If any do come up, feel free to message, hop off mute, however you want to do it. So how do we actually now put this all together and sketch our own cubics? Well, in all cases, these are the key features that we're looking for. We want to find the axes intercepts, both the x and the y. We want to find any endpoints if they exist. You know, this is typically only if you ever have a restricted domain, because if you look at the shape of the cubic, well, this just shoots off to positive and negative infinity. There's no actual inherent endpoints in the cubic unless the domain is explicitly restricted. And the last key feature, the inflection point. So let's have a look at how we can find them all. Easiest one to find off rip is always going to be the inflection point. We can see we have a +1 on the x and a -3 for the y. So that's going to be a shift left by 1 and a shift down by 3. So just like finding the turning point, that will also give us the inflection point of this cubic. Axes intercepts are also quite simple. You're solving those, again, very similar. Setting x equals 0 and y equals 0, respectively. Y-axis intercept, you do x equals 0, simplify, simplify, simplify. There's your intercept. X-axis intercept, y equals 0. This one's a touch harder to do because now you're doing the cubed root of a number as opposed to the square root like you would be used to for quadratics. It's just another root. So the algebra is slightly harder for this, but the fundamentals are still the same. Get everything onto the same side, cube root what's left over, and then get the x back on its own. The procedure would be exactly the same if there was a square there, but this number would be this would be the square root as opposed to the cube root. Okay, we got our inflection point, we label that there. We got our axes intercepts, we label them as we found them. And then all we do from there is just draw the curve that connects all of those points. That's pretty much all there is to that. Once you have all the points labeled, it's kind of hard to mess up the shape of the curve. Like for instance, if you imagine there was no green line there and you just had a dot here, and a dot here, as long as you know the curve is supposed to wobble at this point, you kind of can't mess it up. Like you can't come from up here, for instance, and then also hit these points because, you know, the curve's got to continue in the same direction. So if for whatever reason you forget what rough shape the cubic has to have, just simply dotting out the key features that you have is usually enough to be like, oh, okay, it's just going to follow that sort of shape. Cool, got it. Yeah, if you did have a restricted domain, endpoints are solved the exact same way as solving any other endpoints. Just shove in the x values into your f of x function and get the corresponding y value. And then, yeah, make sure you're using the right dots. So reminder that when it's a square bracket, you use a dark circle to denote that endpoint. And if you have a rounded bracket, then you would use an open circle for that. I have just seen a question come through. Let me see. Are there any scenarios where there could be different shapes of the graph with the same points? With the same points, no, because if the graph is shaped differently, then it would have to curve differently. So it would never have the same shape. Yeah, same points? No, it'll always be the same shape for same points. When you have like a negative, for instance, the only thing that would change would be whether it starts from bottom left or top left, like this here, right? But you can see putting a negative sign on there. Actually, I can eat my words there. This one here, right? Both of these cut at the origin. That's like the only exception we just saw right there. That's kind of funny. They both cut at the origin, but because one was negative, it had to start from the top left and then at the bottom right. Yeah, good question. You were actually right about that. There is one that comes up, although it is the simplest possible scenario. But nice. Good pull. Okay, is that all that's in here? Yeah, okay. That's all that's in here for now. Any other questions as to what's covered in the sketching of the inflection point for cubic? Cool. Okay. That is not the only form of cubic that can be sketched. There are different cubics that will actually have slightly different shapes. Well, I say slightly, this is kind of decently different, to be perfectly honest. It's a bit unlike the quadratic, where it doesn't really matter whether it's factorized or in its turning point form. The quadratic always looks like the quadratic, more or less. The cubic, however, can have significantly different behavior depending on if it's in its factorized form or if it's in its inflection point form. So we're going to now explore the differences between those. So, what are the things you have to consider, just broadly speaking? Oh, hang on a minute. Can we do a practice question on this? Are you talking practice question on the inflection point one? Cool. Yeah, why not? We'll take a break from the lecture and then we'll do a practice question on the inflection point form. Cool. Okay, so for that, what I'll do is I will drop the notes we've just discussed in the chat. Sketching cubics. I'm doing it to your DM again. Ha, I caught it this time. Okay, let's fix that up. Cool, that's that. While I'm at it, I might as well grab the classwork doc. This will cover all of the relevant questions for the Cambridge textbook in this particular lesson. And one we'll have a look at for today as a first practice. We'll just do 1A. It's about as complex as anything else. Cool. So I will now move on to the document camera where I do the handwritten notes. So that'll be back on the main screen for anyone who's first class today. If you haven't already, make sure you give it a pin. That way it's easier for you to access quite quickly. If you have any questions as to locating that window, just let me know. But I will start writing it up. Then we're going to have a look at x plus 2. I guess I don't even have to pick one from the book. They're all the same. I could just sort of make one up if I really wanted to. Okay, cool. So that is the cubic which we will be trying to sketch. On the screen share, I'll leave up the... There isn't really a procedure for this one actually, so I guess I'll just keep the example up that we had, and you can follow the main key features, which is we want to find our intercept, we want to find our inflection point. You also have a copy of that in the chat. If you don't want to switch between the Zoom screens, you can check the PDF for the notes that we have on the screen share. Cool. All right, give you guys a second to get sorted. In the meantime, is anyone ready to start me off on how we might sketch this?
Would you find the inflection point first?
Sure, why not? Seems pretty easy to me. The fastest thing to do.
Which would be -2, 1.
Yeah, almost. -2 and...
Oh, sorry, -2, -1.
-2 and -1, yeah. Why is that?
Because with the y, you just kind of take it as is, whereas for the x, it's the other way.
Yeah, that's right. So you're looking at these two numbers specifically. The x1 gets reversed, the y1 stays exactly as is. Perfect. That's 1 down, 2 to go.
And then find the intercepts.
Yep. What's that going to look like?
Probably just start with setting x to 0.
Yep.
So you just get, if x is equal to 0, you just get y equals -1.
Y equals what, sorry?
Y equals -1.
So x equals 0 doesn't mean the whole bracket goes to 0.
Oh, sorry, my bad. That would be 7.
Yeah, so 2 cubed gets you
to. Set it to 0.
Yeah. I know what you did. It's cool. Yeah, so that gives us our y-intercept. And yeah, only one left, x-intercept, which is how?
Because you're setting y equals to 0, you'd rearrange to get 1 equals what is left.
Yeah, so we're going to have that. 1 equals whatever's left is correct, yeah.
Would you cube root both sides here?
Sounds pretty good to me, yeah. What's the cube root of 1?
Just 1.
Yeah, that's it. 1's the easiest number to have there. And then
Just minus 2 from both sides.
That's going to be x equals minus 1. Cool. Alright, I'll just pause for a bit. So we've done our inflection point, we've done our x and y intercepts. The only thing that's probably a bit new is the inflection point, but again, just sort of imagine, for those who are still following along, that's basically just the quadratic turning point form rules. And x and y intercepts, that should also be similar. Anyone have any questions on those key features so far? Or maybe even like the cube root, that might be a bit new for people. Any questions at all? Sweet, alright. Nothing left to it but just dotting everything out now. So let's dot out our inflection point, -2, -1. We got a y-intercept of 7, x-intercept of -1. So I'm deliberately leaving the points there. What's this curve going to look like if anyone could describe it roughly?
Would it come up from the bottom left?
Mm-hmm.
And then, like, that's the inflection point, so you'd have a kind of bit of the curve there. And then come back up through the x-intercept and into the y-intercepts.
Yeah, exactly. So like, the easiest bit by far is to see this. So if you know this is an inflection point, it's got to come up and hit these. And well, once you have this part of the graph, the rest of it follows. That's like at a very basic level. If you like blank in the exam, you're like, okay, I know I've got to connect these points at least. So you can draw that bit. And then that might jog your memory to be like, okay, I've got to continue the curve that way. But you know, ideally we don't ever have that situation, and you just know the graph, so you can very quickly smash it out. This is pretty much exactly what your working out would look like. You would be able to immediately identify inflection point without any real working. Couple lines for y-intercept, couple lines for x-intercept. This might be a bit nasty, like for instance, even just having a 2 here, you're now going to have the cube root of 2, which you can't simplify any further, and then your number becomes, instead of that, you now have the cube root of 2 minus 2, and you would simply label that exactly as written, cube root of 2 minus 2. Probably worth touching on it at this point now. Being able to estimate whether this is a positive or negative number starts to matter a little bit, but not by too much, because if you think about, like, looking at this number, might be a bit hard to know whether it's positive or negative. It's probably worse if I do like a minus 1.5 here, like that makes it really strange to figure out, to estimate. But let's just pretend I don't know what that is. The fact that I have a y-intercept of 7 means I kind of just have to have it somewhere in here. I'm never going to have it in the positive region, because then I have to do like this to get it, and that's just not going to really happen. So sometimes in other graphs you kind of have to be able to estimate these things. For cubics it's a bit more forgiving, because there's no way you're going to draw this. You know, as soon as the y-intercept is very clear, and the y-intercept will always be clear. Right, cubing a number will always give you a nice thing. Cube rooting a number will not necessarily give you a nice thing. So yeah, just using a bit of inference of being like, yep, that one's there, it's got to come through that negative side. Any questions about that little ramble? Cool, okay. Yeah, that's inflection point cubics. Next up would be the factorized cubics. So let's head on back to the screen share portion. Cool, okay. So, factorized cubics, what's going on there? Essentially, you're going to have a sequence of terms that are multiplied together, kind of similar to how you might expect a quadratic to look, except instead of having 2 terms, you might have up to 3 terms for a cubic. What do we actually care about in this circumstance? One of them is going to be the sign of the overall cubic, whether it's a net positive or a net negative cubic. That'll be like our reflection that we look at. Whether it has linear terms in the sequence, or whether it has repeated linear terms in the sequence, which we'll explain a bit more in detail what that actually means. And basically we're going to use that information to figure out where are my axes intercepts, and what's the overall shape going to look like. The reason it gives you axes intercepts is the same reason that the factorized form of the quadratic gives you axes intercepts. When you set y equals 0, you now have null factor law. Right, like if you put a 0 here, the x-intercepts are achieved by the null factor law of each of those individual terms. So getting the x-intercepts is simple as just going 1, -2, 3, just based off of solving each of these for 0. Y-intercept is also trivial, x equals 0, and then multiply everything across, and we're pretty much sorted. All we have to do now is figure out the overall shape of it, whether it's a net positive cubic or a net negative cubic. And the way you do that is by looking at the signs of the x terms in your function, and there might also be a negative at the front of it as well, up here. You're essentially going to imagine expanding it all the way out, and then infer what the net sign would be. You got a positive x here, a positive x here, a positive x here. 3 positives stay as positive when it comes to the sign analysis. You wouldn't want to actually go out of your way to expand it. That's a lot of time wasting in a SAC. But if, for whatever reason, the sign analysis stuff is a bit challenging, at least while you're practicing it, you might consider expanding it on your CAS just to prove to yourself, yep, I got it right. My guess was correct. Whether it's positive or negative behaves exactly the same as the inflection point form. So positive will always start bottom left and end top right. Negative will be the opposite. And we'll see what that looks like here. So you can see it always starts bottom left and ends top right when it's positive. Even though there's a bit of weirdness going on in here, the overall idea of the cubic starting at the bottom left and ending at the top right is maintained because it's positive. As for everything else that goes on, well, you would just dot out all the key features that we solved. So we solved there was a -2 here, there was a 6 here, 1 and 3. Those all came from all of these things that we solved here. And once you dot it out and know where to start, you kind of just follow your nose and then just draw a curve that's smooth, connecting all of those key features. That's the gist of it there. Before I get into some weird nuances, is it fair enough, the overall approach to what we're doing here?
Wait, so do you just kind of, because you've got the x-intercepts and just the one y-intercept, do you just kind of just eyeball it, like when you just draw the graph?
Yeah, precisely. As long as you're hitting all these key features, that's the bit that matters most.
Yeah. Would it need to be like reasonably to, like obviously it won't be to scale like exactly, but would it need to just be reasonably within the range of what the graph could look like?
Well, you can't really mess this up because you set your own scales every time you draw this.
Yeah.
There's only a very few, like maybe in an exam they might give you a scale that already exists, but because you set your own scale, what your y-axis scale is doesn't actually have to be the same as your x-axis scale. Like your y-axis could be counting up in 5s, 10s, whatever, and your x-axis could be counting in 1s and 2s. So you can't actually get the shape wrong unless you're clearly just not hitting the key features or doing some deliberately weird shit, like doing more curves than you really need to. As long as you're doing your reasonable best to draw a smooth thing that does as minimal number of curves as possible to connect all the points, you're fine with shape. And I kind of detail this in more, I go into more detail in this here, which is like why aren't we labeling turning points, for instance? We needed to do it for quadratics, why aren't we doing it here? Surprisingly, finding those turning points is a reasonably challenging ordeal, oddly enough. You actually have to go all the way to the calculus section of methods before you can actually find those. And when you do get up to calculus, you'll realize that the amount of work it would take to do that, at least by hand, looks like this. So from here, that's the working, doing a bit of factorizing, getting your coordinate, getting your other coordinate. It's a reasonably difficult amount of work. 3, 6. Hey?
Yeah, I was gonna ask, is that the stuff about like when you set something about the derivative and then you find the stationary point,
Yeah.
like where it's equal to 0?
Yeah, precisely. So if you've seen it before, I'll just briefly touch it. You'd have to or want to expand your function out so it's easy to solve the derivative of it. And then from there, derivative 0, solve, and then get the corresponding y values. So almost about it, if you count the actual number of lines, it's probably something like 15 lines of work to get it. These never show up tech-free. You might do it tech-active, but at that point you don't even really need calculus because you can just use the graph tools to find everything you need. Only reason I'm showing that is to show you why you don't have to find those turning points anymore. And because you don't have to find them, like, it gets a bit weird. Like, for instance, having a turning point in the wrong bit. Like, if I draw another potential way to draw this graph, an incorrect way, but one that could happen because we're not finding those turning points. If I go to the handwritten bit now and label the exact same key features, you kind of have to go out of your way to make it bad, but something that might happen if the numbers are different, you could potentially do something like this. Yeah, if the scale was different, maybe I'll bring this closer so it doesn't look as weird. Like if you're really careless about your scale, you might get something like this where you actually draw your turning point on the entire wrong side of the graph. So just pay a bit of attention to your x-axis scale. Try not to make it like so. Try to keep it consistent either side of it to avoid putting this turning point in the wrong spot. That'd be the main thing to watch out for. But, you know, if you have it scaled out properly, it's really hard. As you saw, I had to draw it really stupidly to make it happen with a reasonable scale. So it's pretty unlikely to happen, but I just wanted to show you ways to avoid that without necessarily needing to find the turning point.
But you probably wouldn't lose marks for a scale as long as it's like clearly hitting the right points, right?
Yeah, this is where I'm like ambiguous. I think you should be fine still. Yeah. Because what I said about the scaling between the x and the y axis, those can be independent. Like this one could be like 50 for all we care, but along the same axis, you want to try and keep the same scale. Yeah, it's about 50-50, I think it's going to be. I haven't come across an examiner's report that has ever complained about this. I think I'm just kind of bringing this up because I see it as a potential issue, not necessarily that's an issue that's ever really come up. Just thought I'd prepare for it, but this should never be a real worry. Just take-home message would be make your axes reasonably scaled properly, and everything else should follow suit. But okay, cool. That was a tangent. Next up, we'll have a look at what happens if you have a negative cubic. How will you know if it's a negative cubic? Well, that'll be dependent on the sign analysis of the overall cubic. So you can see we have x, x, and negative x. That's one of the things they do a bit sneakily in here. They don't actually, at least in the book, they don't put the negative sign at the front of the function. They kind of hide it in the factor a little bit. So you might look at this like immediately and be like, oh yeah, cool, no negative, should be positive. Make sure you go out of your way to actually count the x's that are in there, because some of them might actually be negative with that thing factored in there. So for the sign analysis on that, when you have a mismatch, a non-even number, you end up with a net negative cubic, but everything else is the same. X-intercept let y equal 0, y-intercept let x equal 0. We have all our key features. Negatives will start at the top left and end at the bottom right. Again, just try to draw your thing with as little curves as possible. And yeah, just connect all the dots. Fair enough?
Since when x is positive it starts from bottom left, and when it's negative starts from the top left, what would be kind of a reason why it would start? Is there a reason it would start from, say, the top right or the bottom right? Like, what would change in the equation for that to happen?
Yeah, I mean, that's just an interpretation of whether you look left or whether you start looking from left or start looking from right. Like, starting at the bottom right, I mean, that would just mean going backwards.
Yeah.
Yeah, because you'll never draw it here and then go over there. You'll just shift your axes over accordingly to make it work.
Yeah.
But no, it's a good question. The last thing that's a bit strange about this one is the repeated linear factor. So that's referring to this term here. It's a linear factor x minus 2, but there's other copy of it, specifically one other copy of it. Everything is solved the same way. What's worth pointing out is that x now counts for double. Alright, there's 2 of them in there, so make sure that that counts as well. Double x and a third x, net positive. Now, the other thing that matters here is instead of having 3 x-intercepts, we now have 2. Because of that, and for other reasons, the term that has the repeated linear on it ends up being a turning point on the x-axis specifically. So this one gave rise to x equals 2 as our solution. That is now going to be a turning point on our graph instead. Yeah, that's the only thing to watch out for. It's positive, so it starts bottom left, ends top right. It cuts through all these key features. You just got to keep in mind that the one that you turn on is going to be the one that has the square on the term. This is still hard to break as well, because let's say you don't turn here. Let's say you cut through. Well, you know your cubic's got to end at the top right. So if you do cut through, you know you've got to cut back through again. But you don't have another x-intercept to cut through. That should be a warning sign in your mind to say, oh shit, I've done something weird. That's the first thing. The other thing is, what if I turn here instead? If you turn at the wrong spot, there's no way you ever hit your y-intercept in time. Like if you turn here, for instance, you've now got to turn back to hit that y-intercept, and there is no x to accommodate that. So even though I'm making emphasis that you have to turn here, you can't really mess this up, because drawing it any other way would cause you to have points in different spots than you've solved. So if that circumstance comes up, you've either solved the wrong points, or you're trying to draw your graph incorrectly. Key things to watch out for: positive starts bottom left, ends top right. Regular linear are cuts, just like before. Repeated linear are turning points. That's it for that. Any questions about how that one's came to be? Cool. This might be the last one. If we have a negative involved, again, the negative sometimes appears in the factor. That's the sneakiest way it could show up. Everything else is the same though. So it's a net negative cubic because you've got 2 positives and negative. Remember, that counts for 2 positives. X-intercepts, y-intercepts, same as before. Because it's negative, starts at top left, ends at bottom right. The turning point again at -2 because of it coming from here specifically. Okay, there's one more. Sometimes you'll have a quadratic factor in there. A little bit different to a repeated linear, even though a repeated linear is technically a quadratic when you expand it. What I'm more referring to is an irreducible quadratic, in the sense that it can't be factorized further, or at least not in math methods it can't. If any of you are doing spec math, this has complex number solutions, and technically therefore complex factors. We don't need to worry about that for methods though. But a bit of a sneak peek for any method students, any spec students here. That has no solutions if it doesn't have any factors, and so under those circumstances, this term contributes nothing. This is the worst case for anyone that has to do this by hand. And the reason why is because this is by far the worst case of just freehanding things. you kind of just do a bit of a wobble, and as long as it goes through the things that you know it has to go through, like for instance it's negative, so it's got to start top left and end bottom right, and we knew we had one x-intercept, one y-intercept. As long as we go through those points and make it the curve overall right, you really just kind of got to guess what this middle bit looks like. Without a CAS, or without going overboard with solving each individual dot on the graph, you really just got to guess what this wobble looks like. It's the worst case scenario, pretty much never shows up because of that in a tech free. Tech active, obviously you just graph it on the CAS, so you're fine. But just worth pointing out, just in case a book or otherwise gets it. So I'll reiterate, as long as you're hitting the things that are guaranteed, cutting through the x and y that you found, starting top left, ending bottom right, everything else is even more up to interpretation in the middle. Cool. I believe, yeah, I'm not going to, this is for when we hit calculus. We won't worry about going into detail there. That is factorized cubics. So we've got your linear factors, repeated linear factors, and whether it's positive or negative. Those are the key things that you're looking for when solving these kinds of questions. Any conceptual things I should clarify before we do a question live together? Cool. Alright, this one uses the exact same notes, so you guys have the PDF still as well if you want to refer to that. Which one should I show? I guess I'll show them as they come up. Okay, so that's going to be the 6F portion. Oh, by the way, your teacher, when you get into this, your teacher or the book might teach it in the term of sign diagrams. I don't know why they go around and do this. Their idea there is you literally solve individual x and y pairs and then get your curve because you get that. I don't know why they do it. It's such a waste of time. You can see how they're just sort of testing the values and seeing, oh, is it positive, is it negative? Actually no, this is factorization, sorry. But they are doing this sort of sign analysis where they draw this little block of where is the graph positive, where is it negative, where is it zero. You don't need it. It just sort of has to be this way if you follow the things we were describing. I only mention that because some of them might say draw a sign diagram. If your teacher cares about that, obviously draw it for your teacher. But for this will never show up in like a exam. SAC again will be based on your teacher. Cool. Okay. Let's have a look at 1A once again. I'll start writing it out. X bracket x minus 1 bracket x minus 3. Okay. This one will be closest to this example, so I'll leave this one up for reference.
I'm just on the same thing!
By the way, Charlie, your mic's not muted. But cool. Anyway, so I've got it written up, and I've also got on the screen share the most relevant example of what this one would be. Who wants to start us off?
And solve the x-intercepts.
Certainly. Let's knock them out. What are they going to be?
1 and the other one is 3.
Okay. Are there any more?
Would 0 be 1?
Yeah, that's right. Remember, null factor law works for all the multiplied terms in the list. So even though there's no brackets there, that is indeed multiplied along with all of them. Nice. That's all our x-intercepts. Again, that was just null factor law.
And would the y-intercept just be 0 as well, because you've got that x at the start, so...
Yeah. So, bit of a fun fact. If you ever have x equals 0 or y equals 0 in your solution, the other pair to that is always going to be x or y equals 0. For if you get it in this sort of thing. That's the only way that ends up working. But yeah, so just to show the working out as to why that would work. you have a 0 when you sub in x equals 0. So whatever this ends up being doesn't matter. You got a multiplier of 0. Nice. We got x-intercepts, we got y-intercepts. That's pretty much everything. Only one thing left to do.
Hi. The group thing. Yeah. Sorry. Thanks. The math thing.
What else we got? We got x-intercepts, we got y-intercepts.
You got to figure out like the final sign of the x, so whether it will be positive or negative.
Yeah, that's right. That's going to help us at getting our shape going.
And it would be positive since there's no negative.
That's it. Positive, positive, positive. The sign analysis there gets us a net positive. So what does that tell us about what we're going to end up with?
That the graph's going to start from the bottom left and then move up towards the top right.
Sounds pretty good to me. So I'm just labeling all the things for now. We got the 1, we got the 3, we got the 0, 0. And as you said, yeah, starts bottom left. And if we try to draw this in as few curves as possible, we get maybe not a nice cubic, but an overall cubic shape. That's about it, yeah. It is like worth doubly highlighting that negative analysis does matter, because another way you could connect those points would be like this, which is incorrect. You do want to make sure that you're checking whether it's positive or negative.
Where are you going? All right.
Sweet. Yeah, so that's one example of the factorized things there. Anything to clarify on that example we just had a look at? We'll look at a few more. Okay. Question 2, if you just have a look at it, I'm not actually going to get you to do it. Sometimes they won't give you a factorized form of the cubic, but because it's in its polynomial form, one of the things I didn't quite mention is that you can't really, there's no like equivalent completing the square for a cubic. You can't really get it to look like a inflection point form cubic without special case scenarios. I haven't actually looked into it or read into it. I'm sure there's definitely some ways you can figure out how to complete the, well, I guess complete the cube for a cubic. But it's beyond the study design of methods to actually achieve that. So the good news is, at least when you have this polynomial form cubic, there's only one thing you can do to it, and that is to try and factorize it, not try to complete the cube. So using the methods we've discussed earlier, if for whatever reason you get this, which would be really nasty, you'd be doing stuff like factor theorem to try and do your initial factor, polynomial division, get the other terms, and just eventually make it look like one of these. That will be the goal. That's going to take a while. Actually, we've got 15. Nah, that'll take too long. Better we have a look at a new, well, not new, but a different example. So I'll get up another example. This one's going to have a different shape to it. Okay, that'll be 3a. Y equals x minus 1, x minus 2 all squared. Yeah, I'll keep the relevant thing up as well. I was debating whether I should let you guys determine what example it, yeah, that's fine. While we're learning, we'll use all the notes and resources that we have access to. Cool. On the screen share is the relevant example type that we have, or if you just want to see how much you remember, feel free. Once you're ready, how shall we start?
Find the y-intercept first.
Mm-hmm. How are we going to do that?
So that x equals 0,
Mm-hmm.
so you'd get -1.
Let's find out. So You get
Oh, as
-1
in
on the
like I'm
first
just
bit.
looking through. Yeah,
Yeah.
that's what I meant.
-2 on the
Negative.
second. Yep.
So you get -1 times 4, which is just -4.
Yeah. We're gonna get y equals -4. Nice. Alright, y-intercept achieved. What else?
Now to find the x-intercept.
Yep,
So you'd have to set the y equal to 0, and then you can use null factor.
that's pretty good. Yeah, I'll write that out. Null factor law gives us...
So your first solution is 1,
Yeah,
and the second one is... Sorry, I'm blanking.
that's fine. So think about the fundamental. Null factor law just means this equals 0 or this equals 0.
Would it be just 2?
Yeah, it'll be 2.
Yeah.
So...
Sorry, I don't know what's complicating that.
Nah, it's fine. It's fine because like it looks different sometimes. Sometimes you blank. So a good little lesson here: if you are blanking, just go back to fundamentals, which means that each of the terms have to equal 0. In which case you just grab the entire thing, make it 0, and just solve for x. So that'll be a matter of square rooting that, and then 2 goes to the other side. There is, once we see it, there's an obvious hack, which is just flip that term and you're fine. That works in most cases. Just make sure there's no number here as well. If you flip it there, then that's going to break a little bit. You just got to figure out what would cause the term to go to 0. It's not necessarily always just a flip of that. But that's fine. That's that, that's that, that's that. We have all of the key features to dot out. Now it's just a matter of what? What else are we missing?
I think I remember something about... I think this is a repeated linear factor, the second
Certainly is.
second part, x minus 2 squared.
Yeah. Why does that matter?
I think it's a turning point.
You think correctly. Yeah, it's going to be a turning point. So whether you do it, whether you write it out as a turning point, as a reminder to yourself or not, isn't really required. As long as you draw it as a turning point on the graph, you're fine. But yeah, okay, so we got our x equals 1, we got our x equals 2, we got our y equals -4. It's all dotted out. There's only one thing left to decide after that, which is where's the graph going to start?
From the bottom left, because
Mhm.
there's no negative x's.
Yeah. So I guess more specifically, it's the sign analysis. Like for instance, if there was a negative in here, that still wouldn't matter because double negative makes positive, and then another positive stays positive. So it's a little bit more about the net result rather than if there's negatives or not. But I think you already knew that. Just wanted to clarify further. Yeah, so we know it's positive, so it's got to start bottom left and end top right. So with that in mind, we know we have to cut through our intercepts, and as you said before, we have to turn here. This is what I was talking about earlier in the sense of, I should go like this a bit. If you do cut through here by accident, you know, if you just kept going, you've drawn a quadratic, and you're like, okay, well that's clearly not right. So you would probably then be like, okay, well I've got to curve back up, but there's nothing here to actually curve up through. So that'll be your indicator to be like, okay, something's going wrong. I've got to figure out either whether my math is incorrect or whether my graph is incorrect, which in this case the graph is incorrect. Let me try and draw that properly, dear God. There we go. Still missed a 1, but I think you guys get the point. Yeah, that is that example. That's pretty much it. I've noticed the only negative that I can see as an example was one of the expanded versions. So we won't quite get a chance to look at a negative example because I do have to bring up one more topic for our lecture portion. But the only thing that the negative changes is whether or not you're starting from the top or bottom for the left hand side, so that shouldn't be too much of a stretch to figure out. Oh yeah, there's also the 4a. We may or may not have time to do this. Let me quickly touch on the last lecture portion. It'll be very quick. We won't have a look at an example of it because it's rare to show up, but I figure it's still worth touching on. So, back to the screen share. Just like how there are inequalities for linear and quadratics, there's also inequalities for polynomials as well, which is basically just saying, is this greater than or less than some other number? If you guys have done inequalities with quadratics before, there's a couple of methods that you could have used. The one that I'm going to propose here specifically is to literally just sketch the graph and then look, is it above 0 or is it below 0? And you can very clearly see the range of x values, or I guess I should say the domain of x values that accommodate that. In fact, I'm literally using a quadratic in this example to show you that it applies to literally all the polynomials. Because you guys already have this skill of being able to sketch, or at least you should eventually have this skill of sketching a polynomial. So rather than try to learn a new way of solving inequality specifically, better instead to leverage your abilities of sketching and then go from there instead. So how's it work? This is a nasty example. You got a quadratic on one side, less than a linear on the other side. The first goal is always to get it to quote unquote equal 0. It doesn't actually equal, but basically whether it's a less than, greater than, whatever the actual sign is, get 0 on the other side. Then this thing that you end up with, you sketch. In this case I'm using quadratic formula because there were no nice factors for this. To get the x-intercepts, turning point is just the middle point of all of that. I won't go into too many details. We all know it's like, you know, axis symmetry, completing the square, midpoint of the x-intercepts. Any method by which you want to solve quadratics is how you do that. You sketch that graph, and because you got it in a stage where it said this, less than 0, it just means that anywhere the graph is negative, which is what less than 0 means, that domain of values is what matters the most. That is your solution to all the x values where the graph is negative, less than 0. That's pretty much it. Get everything on one side of the inequality, sketch that quadratic or polynomial, whatever it is, and yeah, is it above or below? That'll depend on whether you're doing a less than or a greater than sign. That's pretty much it. If you have a look at the actual section on this, it's literally that big. Like, you've got the factored versions and the inflection point. They're trying to get you to literally sketch it to use this method. And here's the other examples where you had to have it on both sides and do a bit of rearranging. It's a very short bit. I've never seen it show up in an exam at all. Cool, okay. I think I got through that in time. If there's any questions about that, I'll take them. But I think looking at this, or even... oh, I guess they're both the same actually. That's why they've cased it, actually. Yeah, that's interesting. When you have the quadratic term in there, none of these quadratics have solutions. And just by looking at this, this is like, you're not going to see this unless you go through really advanced methods of solving things or just looking at it on the CAS. Like, you would have no idea that this one is a wobble, a small, it's not really even an inflection point, it kind of just does. Like, that first example does this, but this second example apparently has 2 turning points. Doing a tech free, you're just not going to find that out. So I think maybe just to wrap this one up, I'll show both of those on the CAS to see how there's really no, without using calculus or other methods, you're not really going to get too much insight into that, so you really just got to freehand it as best you can, which is why they don't show them tech free. So let's have a look. If we do our bracket x minus 1, bracket x squared plus 1, we can see that factor there, that's going to have no solutions. You'd have x squared plus 1 equals 0, and, well, you'd be trying to square root a negative number, which is just not going to happen. So we would expect this to cut at 1, and then do nothing else really. Well, obviously the y-intercept, you try to find that, and the fact that it's positive, we can use all of those to determine the rough shape, but it's just going to be this middle bit that's going to be the most confusing. Because literally all I do here is change that to a 2. Yeah, this should still do it. The other, I'm looking at 4b, which does look a bit different, but I think this should be enough to still mess it up a bit. No, it doesn't. Okay. I guess I do have to write it out exactly as I had it. Oh, jeez. Completely different. Set our scale a bit differently. Or a lot differently. God. What, 50? Usually you can zoom fit, but some of them, yeah, some of them do that. Oh yeah, there we go. Found it. So we can I get this out of the way? I can. Drag it. No. That'll do. So, it's really hard to know what's going on in that middle point without a CAS or without using calculus. For those who would be using calculus, you would be trying to do derivative 0 to figure it out, but we already saw in a tech-free way that's just a lot of work, which is why it won't really show up. Cool. Okay, that's pretty much all the key examples. I guess we do have time to have a look at the inequality bit, so let's give that a shot instead. Okay. So I'll do the one that's a bit tougher when you do a little bit of rearranging. So let's try the part B. X cubed is less than 5x squared. What I'll do while you guys are thinking about what to do, I'll put the relevant notes up in the chat. These are a little bit different, but still the same idea. You still want to try and sketch what you've got. Alright, that's in the chat, so if you need to have a look at it, feel free. Otherwise, if you've got an idea of how we might start, let me know.
Rearranging to get a 0 on one side.
Yep, sounds pretty good to me.
So you could just minus 5x squared.
Sounds pretty good, yeah. Minus 5x squared, less than 0. Cool.
And then I think you need to graph it.
We do need to graph it, yeah. We're going to run into a little bit of an issue, which is I haven't explicitly told you what to do, at least in the lecture portion, to sketch this, but I think I briefly mentioned it when I talked about this. Looks a bit different to our other graphs. How are we going to make it look more the same?
Wait, since it's a cubic, wouldn't you need every degree of the power? So I'm not sure what that would look like, but because you've got x cubed, x squared, but no x.
Yeah, okay, fair enough. You don't need all the terms. Kind of like how x squared plus 2 is still a quadratic. You don't need the x in there.
Okay.
Same thing applies here. The challenge we have is sketching polynomial form, even in quadratics. Like you wouldn't want to sketch x squared plus 2x plus 3. No one knows what that looks like until it's factorized or until it's completed square. We've got to do something to this to make it look easier to sketch. And there's one thing that's immediately available.
Would we take x squared out as a common factor?
There we go.
Yeah.
X squared out as a common factor is exactly right. Yeah. X squared out as a common factor, and all of a sudden, if we just look at what we're left over, that, if we just sort of blank out that, we know how to sketch that now. Or at least we use the techniques that we've had a look at to sketch this. We're going to run over time. Yeah, why not? You guys can finish it off if you want to stick around. I won't speed through it. How do we finish this?
Well, now we have our two intercepts, 0 as a repeated factor and 5.
Yeah, x equals 0, x equals 5 from same techniques as before. Yep. What else?
And there's, well, now we can sketch it and there's no negative, so we start from the bottom left.
Yep, starting bottom left. We got a cut at 0, which also gives us our y equals 0. And we got a 5. And then, yeah, as he said, we got a turn at 0 because of the repeated linear. And that gets us our sketch. Now, that does help us a lot, but the question didn't say sketch. The question said solve this. So how do we now interpret our results?
I guess you look for what values of x have y's above 0.
Below 0 for this one.
Oh, sorry, below 0.
Yeah, same idea. So, what's that going to end up being?
Between 0 to 5.
0 to 5 is one set, yeah? So you're saying that these are negative?
Oh, sorry, anything below 5.
That's still mostly correct.
Or including 5.
Just quickly check that inequality again. So that symbol, is that an inclusive or an exclusive?
Exclusive, so anything below x equals 5.
Super close. Something
Oh, okay, yeah, excluding 0. Okay.
yeah, excluding 5 and 0. Yeah. So how would you do that? You would do x is an element of negative infinity to 5 non-inclusive, and then you would do your little backslash 0, because that backslash means well, technically it means a set difference, but for our intents and purposes it just means excluding 0. Let me just double check that again. So negative infinity to 5 is good, non-inclusive, non-inclusive, and we're also cutting out the 0. It's in the middle. Yeah, that looks good. Sweet. And yeah, again, we're just looking, where do we have negative y? Awesome. Alright, happy to stick around if you guys have any more clarifications or any other quick questions. Otherwise, thanks for coming. Enjoy the rest of your day.
Okay.
Thanks.
Thank you.